Well, welcome everyone. Welcome to Math Day. We're really excited that we have some upcoming great talks, but it's my pleasure to introduce the speaker today, Dr. Steve Harnish, who's coming from Bluffton University. He has a bachelor's degree from Goshen College. He has a doctorate in mathematical logic from the University of Illinois. He's taught and presented at international conferences and universities in 4 continents. He's devoted nearly 3 of 4 decades to teaching at Bluffton University, where he's served as a professor and a chair of the department. And he's particularly passionate about mentoring undergraduates in computational research and National Science Foundation funded internships at Bluffton regional universities and national labs. But so with great pleasure, let's welcome our speaker. Okay.
Thank you. Thank you. I'll make sure I have everything set up here for the slides, and looks like we're ready to juggle. So I'm delighted to be here. Thank you for the invitation, and we want to extend back the opportunities to come and speak at our math seminars or Math Pi Day events. Coming up in 10 days, we'll have one. But in any case, this is the topic for the next minutes. And it's on mathematics and juggling, and some of the mathematics of juggling, and some juggling will be shown, but I won't claim to be a performance level juggler, but I am learning, and I'll invite you to do the same if you would wish after hours, or if you want to come up during it, you could, but more afterwards, okay? So this is the theme: patterns, certainty, and creative surprises. I do have to include some kind of a math joke or two. You've probably seen this one, maybe, if you've been in a math class or other. And there are these kinds of ties to, some translation needed for whether I is rational or real. And, this is the question about pi. Come to Pi Day and we can tell you more about that. Mathematics tends to give us certainty. We like proofs, and occasionally we have a really good intuition of what is going to happen and how we can finalize that this result is true, but it's an intuition, and when we try that a miracle occurs, that isn't usually enough. But we still dig into it, and sometimes that intuition is very important, but there is this kind of question about what is happening. I do include just a few of these slides coming from the sciences because of the connection between juggling and both some gravity and angular momentum. But it is this quote by Einstein that I'll end with before we get into it, that we do try to look for the simpler approaches to explaining an answer as teachers, as math teachers, even if it's a fairly deep and complicated result. And this is a high bar to live up to Einstein's kind of intuitions, allowing him to come up to a simpler answer. But what do we understand is the question. And to start off, I'd like to understand more about the audience, you. So first of all, who is here? Do we have some math, and I'll go through a variety. Do we have some high school students by chance coming in here? Or math students at the university? Let's see, if you raise of hand if you're taking a math class. Don't have to be a math major, just taking a math class. Okay. And what classes are you taking? Maybe that's the question. College algebra? Do we have some college algebra? All right, very good. Do we have some pre-calculus, calculus, multivariate, upper level math courses, some of you? Statistics? Some other kind of general education math or a kind of conceptual math? Okay, good. So who is a juggler? How many of you have juggled something? You've tried. Okay, so good. There'll be opportunity to come up afterwards, as I would say. If you'd like to learn more, though, all of you can hear some of the pointers, and maybe you'll pick it up. So this is an odd question. Are people just born to be jugglers? I'm asking that for a reason as we look at math and juggling. Well, if we haven't tried, we wouldn't know either, right? So, we do have to try. How many types of jugglers are there? Well, there could be the question of how many different kinds of juggling. And maybe some of you have looked into this, but as I dig into it to learn more, there is joggling, which I won't demonstrate. And there is bouncing the juggling balls. And you've probably seen that. I will show you a few videos of what some others do with this. And different props are used, right? And we'll talk about that. There are many different kinds. So I'll ask this question then related to math. How many types of math students, teachers, researchers are there for just posing a question? Thinking about that. There's lots of kinds of juggles, juggling patterns, juggling forms, and jugglers. But that is just something to think about on the math side. So what about the speaker? Okay, so about me. What classes do I teach? A wide range. I've taught the college algebra, basic math, high school kind of level math up through advanced level. So if I would look, what I'm doing right now, teaching some calculus and multivariate. Also in the fall, taught some general education conceptual physics, so that feeds into some of the perspectives of what I'll be sharing. In 2015, I was here just starting off with more of that physical world studies, as well as the basic upper levels. 2005 was a time that was a lot of, for the general audience, conceptual math applied in different areas. But I'll have to admit it, I'm feeling my age. This goes back a while. In 1995, I was in Franciscan College close to Philadelphia called Newman College, teaching college algebra and some calculus. In 1985, I was teaching. But I could ask the question, what classes do you think I taught then? And it wasn't math. You'd have no way of guessing. This was in China, where I was teaching conversational English. And that's when I started teaching at the collegiate level. So that's why I do have this perspective of having seen a lot of different students in a lot of different settings, and want to emphasize the importance of thinking how we all can bring our own strengths to the interests of your studies. So I have given a few presentations, probably about 9 or 10, locally and at regional and national conferences. But these were math conferences. I talked about the mathematics of it, and I would demonstrate it. And so if I would ask the question then, am I a juggler? I would say I can juggle, but I'm not a performance juggler. I'm a mathematician who can juggle, who likes to learn new things about this. But I've kind of brushed this one off after some recent talks, after a few years. And just maybe last week, I tried to push myself to do a simple extension beyond the 3-ball cascade. So I will not claim to be a high-level performance juggler. I will show you and demonstrate some of what others can do and the math of it. And that's my focus. I hope that allows you, if I demonstrate being a learner in this, to consider coming up and trying it yourself, too, as a learner. So are math people just born that way, kind of similar to the juggling question? For juggling, we probably have no idea. We usually don't ask that question. We often have this feeling that I'm not a math person. I am a math person, right? Have you ever heard this? Somebody say, oh, I'm just not good at math. Well, I would just encourage you to get away from that mindset. Carol Dweck talks about a fixed trait mindset, like we're like this level of ability in this area. In my English, in my writing, my math, it's just fixed. I'm never going to be good, I'll change that. She also talks about how there's a growth mindset. So that you're at this level, you might have a range, maybe not shoot the moon, never quite going to dunk that basketball at my height, but there's a range of potential, and you each have potential to grow into whatever level you are with whatever, whether it's a sport, musical instrument, or in your mathematics, right? So it's just a little bit of motivation on the educational psychology kinds of ways. So I will go to this. I'd say, no, they're not born that way. There are many different types. And what type of a math student, teacher, researcher am I? Here's a quick tie into math and educational psychology. Just this quick comment, there are labels out there, and I encourage you to consider going beyond quick labels. Are you a math person or not? I doubt that you've seen a KVA, but do some of you identify as being more kinesthetic, kinetic in your learning, visual in your learning, or auditory in your learning? I would probably say that this one comes more naturally, so maybe some movement comes naturally to me at a kind of easily controlled conscious level. This goes a little deeper, the visual, but I see a certain beauty in the visual. I like to look at that level. And the auditory is something that's a little bit deeper, subconscious, that takes some practice to get ready for a talk, right? So this is how I'd call myself. If you would have such a category, I've seen some educational psychologists deal with that, you might have an A here or a B. So you have 3 choices on the first. After you've chosen one, you have 2 choices left. And after that's chosen, you have 1. So it's 3 times 2 times 1. There's 6 types of categories by that. I would never hold too much stake in your own label of yourself or what somebody else has labeled you in terms of your abilities, kinesthetically, visually, or auditorily, or you think you're always left-handed, can't juggle. I bet with practice you could. So we don't want to get too far into a deep identification with a label, but there would be 6 here. Any of you recognize these, just as a show of hands? Anybody recognize such a identification? What is this called? Myers-Briggs test? Yes. So if you look into psychology of an individual, are you extroverted or introverted? Are you intuitive versus intuitive and feeling or thinking, and also here in this case perceiving versus sensing. There are 2 choices for each of these, and if you look at that, that would be 2 times 2 times 2 times 2. There are 16 categories of individuals if you want to go by that label. So there's a lot of different personal things you bring to any field, any study, and I just encourage you to think about your own strengths. So my strengths through a strengths finder from Clifton is connect, learn, achieve, strategy, ideation. And we're about done with this kind of overview of the types of juggling, the types of math, but you might find a theme that I am connecting a lot. I do like to learn. There's that achieving, but I rather connect in relationships than show myself up over another. So there's this kind of personal dynamic in a classroom where I encourage that kind of view of that relational and the multiple strengths that anyone can bring. Here's a mathematics question before we see the juggling. So Clifton Strengths says there's 4 domains, 34 themes. Here's 5 of them that I've chosen. If you would think of how many different ways you could pick your top theme, for me it's connectedness, there's 34 choices there. Then when I picked one, there's 33 possible here, 32, 31, 30, and you multiply them together, where are we? How big? You know, if you had the time, you could do the math. It's over 33 million. That's about the population of Canada. So this is, you don't want to get too in the thicket of saying, I am only this. And chances are you're not going to see a direct kind of identity that really there's not a tie or something that complicates it more. But there's a lot of individuality. And I encourage you in your sense of like what you are attracted to, of how, as I chair the science department and meet with prospective students, I look for the strengths that that student could bring, or talk about the way in which a team can offer those kinds of strengths. So this is that kind of counting the different kinds of ways you can do things, counting the different kind of uniquenesses to your strengths, and building on those. So here's one that gets closer to mathematics. Who is a math person? Can you look at a family and, I could ask the question, do you identify as like maybe for math day, you're all math people, but also maybe some of you, because you're taking the classes, you've also not majored in that kind of love of mathematics on a major way every day of your life. Here are 3 individuals, they're brothers, Roger, Oliver, and Jonathan. And in early years from this family in England, who knows what would have happened in terms of the studies of these 3 individuals. Oliver was the oldest. He became a theoretical physicist. He was considered like a high IQ. course, with Carol Dweck, I'd encourage you to think that you have strength beyond a label of a number. Jonathan was a grandmaster chess player. In this family, he was just very strategic, did very well. Roger, he could have flunked out of math. In fact, in grade school, he was getting 40s, 50%, and he was held back a year. But there was one thing. He had a teacher. So I don't know, how many of you are teachers? Let's just see a show of hands, get a sense of the room. And so in whatever ways, as a teacher, we have a very important role of helping people to try something or to learn that they've got more potential than they think. So for Mr. Stennett, the Roger finally encountered, I think, in London, Ontario, when family went to Canada. He saw potential in Roger. Said, well, you know, you can do this. You're getting 40s or 50s, but you seem to understand that you just need more time. Do you want to stay after recess or during recess and take the test? And then he was getting 90s or 100s. So this is the person. Anybody recognize him? If you're a math person, maybe, but maybe not. It's more of the physics world. Roger Penrose is the name. You might recognize some of these aperiodic and other kinds of special tilings in his connections to M.C. Escher. He also had conceived of this. I don't know if you've seen that shape. It's impossible to conceive in the position it is right now. You think it could be possible to have three sides connected that way, but then they don't really line up. It's a tri-bar. That's a special insight that Roger Penrose came up with this. Influenced Escher in some of his art. So he's very gifted, has achieved, got his degree in mathematics and algebra and geometry, but it's all because of Mr. Stennett. So know that you can try to go beyond what label we might give ourselves. Okay, enough for educational psychology. Moving on to math and juggling. We've already talked about my years of studying, or teaching for that matter. And I could ask, what is juggling? So there are individuals like Taylor. Glenn has a Taylor Tries set of videos on YouTube that I'd encourage you to consider connecting with. And I would just maybe check, I'll move this lapel just slightly. Is the audio coming out all right for you? Okay. You can hear it in the back fine. Yeah, very good. Okay, so this is the question, what is juggling? So you could juggle. I've thrown a couple balls, and you can see juggling as when you juggle, maybe most naturally, you see people juggling 3 or 4 or more balls. On the other hand, Glenn encourages you to think juggling is really this. You throw them up, you don't just always catch and continue, you drop them and you pick them up again. As an important motif for also what we do in math. You try the problem, you don't always get it right away, but you pick up and try a new strategy. Another thing that you could say, coming from Dave Finnegan about juggling, is that yes, it's great when you do your juggling and you make the catches, but sometimes it's just a matter that you touched it. And a touch is as good as a catch. It's important for the psychology. And maybe that's similar for mathematics. That the touch, or the connection, the inkling of an idea might be just as good, at least at this stage, as that final catch. You can check your finger. Okay. All right. Well, let's see more juggling. So, yeah, partly with my age mentioned, can you teach a dog, old dog, new tricks? Yes, I am trying to learn new tricks, and I'll share that a bit by the end of the hour. But let's focus on Math Day right now. What is mathematics? Math, you might think, is mostly just calculations. Have you ever heard of math as a science of patterns? Maybe if you're a math teacher from recent decades, you would run across this book. That is a motif that I think is very helpful. There are patterns in shapes called geometry, patterns in numbers, which arithmetic and algebra encompass, or patterns of change as calculus. But you can look at any object, any phenomenon, and talk about the patterns you see. In a way, that's mathematics when you study it in science. I'm going to focus a little bit more broadly than Keith Devlin's definition of math as patterns, when these sub-themes of patterns, certainty, and surprise. The certainty and surprise give us some inkling to, yes, connections between math and juggling that we will see for this, this remaining hour, and also connections to Pascal's triangle and several other, even political coalitions. So who gave me the word certainty and creative surprise? If you would dig into the history of mathematics, you would soon learn about David Hilbert. And in the early 1900s, there was a lot of movement towards thinking, we can solve any problem. We can get a proof for it. We must know, we will know, he would say in German. And in a 1930 conference, kind of as he's towards retirement, he gives that word. Same year, same conference, this fellow, Kurt Gödel, off to the side at a round table, was giving the first inklings of his work in the Vienna Circle with his interests in the early 1920s and 30s. But he gave incompleteness theorems. There are limits to what can be proven. There are some things that can't be proven until you come up with another assumption or you sift out the choices. You can't prove about all the facts of numbers just on the set of axioms that you have at this point for at least an interesting enough set of like natural number arithmetic. Well, in any case, there's a lot of depth. There's creative surprise that has been seen in the history of mathematics, and there's creative surprise to be found in other areas in juggling. So here is that certainty theme. Are you certain about that? If you go into a high school geometry class and you might be asked to sketch a triangle, and don't you know if you measure with your protractor the measure of all the angles, they add up to what? 180 degrees. It always happens that way. And this is a proof. One of the versions of the kinds of proofs. You generate, first of all, you might construct your triangle with vertices A, B, C, and these angle measures. And then all I need to do is from this base find that this is horizontal, find another horizontal parallel up here. And what is happening then is with some basic work in your high school geometry, you would have learned that this angle measure B will match this ultimate interior angle measure B, A with A, and C, giving us that these measures all add up to a straight line measure of 180 degrees. You could, if you would visualize it better, just extend out and have the corresponding angle A be extended here, B set it out there, and C the opposite. They also, you see, it's 180 degrees. It's just a given fact. We have proven it, and we are certain with mathematics. Okay, so more about this, and into the juggling and mathematics themes. So there are some surprising connections. This picture tells a lot. So I'm going to tell you a little bit about a sketch of overview. If you are interested, I readily, you'll see on slides my email. You reach out, I'll give you more resources. Some of them are listed here. In this picture, you see this picture right here? Comes from an Egyptian tomb of Beni Hassam. And this is one that is about 3,800 years ago. And it's the first depiction of juggling that we know of. So people have been juggling for at least 3,800 years, probably more millennia. And this picture is of a particular image that I'll soon portray with the video of a world record juggling act. So you ask, like, how many could you juggle? Well, I'm not going to get beyond 13 or 14 like our world record holder has done in the cascade approach. But in any case, you've seen other images here. We're going to get a light touch on an important topic called site swap notation. We'll be counting the different ways. This is going to count the different kinds of categories or types of personality or types of strengths. We're counting the different kinds of juggling patterns possible that we'll soon see. There's also even something about a political coalition. In years of politics, you often see which way does a state lean. Is it red? Is it blue? Is it independent? There's actually a connection between this and juggling, or for that matter, some of these images of patterns that we are seeing, these geometric images. I'll touch on that. I'll point you towards it. If you want more, I'll give you the deeper answer on some of that. Okay? So to start off, this is giving an overview, a lot of resources. There's a Scientific American article that helped with some of the 1985 work on site swap notation. Ron Graham, you'll see featured. For me, the first impetus was in the early 2000s. As it were, he was visiting in the University of Dayton, and I saw him give a talk on some of the mathematics of juggling, and that inspired me to do something a little bit later at Miami University. I believe your alma mater, Dr. Kwiatkowski. So in any case, these are good resources. I can tell you more. So a little bit on history, records, maybe implications from physics. What are the limitations of juggling? But then implications from math, mostly today. A few visualizations and some additional surprising connections. There are links here. At this point, I'm going to demonstrate a few. So we have the sense of the deep history. You can look into this more if you check next in something like from Wikipedia, the Juggling World Records. You'll start to see these listings. And this is the individual, Alex Barron from the UK, who has had 14 beanbag throws and catches. And as you can imagine, some of these are larger, and the beanbags are important because they're small enough for him to throw all 14 and to catch all 14 in his two hands. So you do need, there's matters of physical scale and size that are important here. So that's a limit. I'll show you that in a second. 13 beanbag and 15 catches, for example, both him and another, Eric Toll. So you'll see this wide range of like achievements and for the record of how many catches or how many minutes and hours you might keep on juggling, right? By the way, when you see the bowling pin looking things, they're called clubs here, and you can see the kind of records for clubs as well, or rings and others, props like that. So I'm going to go back to that one more time. Here is a quick video of Alex Barron, and this is a 14-ball flash. A flash means he throws up the 14 and he catches the 14 once. So it's just throw 14 each one once and caught once. A qualifying 14 cascade would be if he could throw the 14 each one twice and caught finally ending with all caught twice. So that'd be 20 runs of 28 rather than only 14. And here it is. So let's at least observe the record on how much you can juggle. You can partly see the balls. He does come back and show us how many he's holding in his hands. And I'd have to dig around to see how many times he's been able to do this. At least this is recorded at this instance, where he starts to then drop them all, and you could see that he indeed had those 14 beanbags in his hands. Okay, that's a 14-ball flash. If you want to really see a more of a, nope, I'm going to go back to that one, a more professional set of performances, I would encourage you to go to YouTube and TED Talk. So I won't provide this, but you can see a lot of variation, and I will simply point you there to say that there's a lot to be seen of varieties of approaches, whether you're simply juggling the balls, whether you start moving around in the angle or dropping the balls and bouncing them, and there's a lot of entertainment to be had. And so go seek it out as you wish. You can see the fast and the slow. You can see the different shapes here, a little bit more U-shaped in what he's doing, how much variety is given. So if you wanted to see some professional juggling today, there you are. Somewhat professional, there we go. And these kinds of variations on the theme. So do look into that as you wish, and I'm going to simply leave it at that for the more professional side. Let's go back to, okay. So I've given lots of talks on juggling, as I mentioned, so some locally in 2014, Here was a national meeting. Ron Gran, I talked to him afterwards. He kind of liked the PowerPoint I'd given him and really loved the kind of connection that I'll share with you about some early stories of limits of juggling. But I had a professional juggler, so to speak, or at least more experience than I, accompany me in that. Okay. So anyway, also at Miami University, a couple talks with modular arithmetic, some forums about these patterns I'll talk about. I am going to dwell on this scene for just a bit. It was also in the initial images. You believe that 3 squared plus 4 squared is equal to 5 squared? Is that right? Something you've heard before? Where? Probably a geometry class for Pythagorean triples, Pythagorean relationship. And we might look at other such patterns. Also, in the early slide, I had a 1 plus 3 plus 5 equals. Anybody want to just do the math because it's an exercise you could do in your head. What is 1 plus 3 plus 5? Of course, it's 9. Also, how many odd numbers did I add up? They're all odds, 1, 3, and 5. I added up 3 of them, and I got what? 9, which is 3 squared. So this relationship, I'm going to also say there are many uses of juggling balls. If you look at starting with a 1 by 1 square, that's this orange juggling ball. I'm going to then pull up 3, the next odd number, added to get the 2 by 2 square, or then I can get these nice orange themed juggling balls for you to be stacked, if they want to stay up, as an additional set of 5 that make that 3 by 3 square. So there are visual proofs by pictures that you can come up with for some of these results. You also prove with mathematical induction how the sum of the first 3 odd numbers is what? 3 squared. The sum of the first 4 odd numbers is what? 4 squared. Okay? So more about that. You'll see it in the what remains of some patterns of mathematics and juggling. So I'm going to dwell a little bit on this original talk in Miami, University of Miami in 2007, juggling sequences with number theory. And it's going back into the history of some stories, a tale of 2 kingdoms. Okay? So we'll learn a little bit about that. Here is a place to start. We're looking for patterns in some numbers, and we'll look at some patterns in the number of juggling forms you can make with so many balls in these patterns. I'm first of all going to say, do you see a pattern in these numbers? 1, 3, 6, 10, and 15. I'll just lay that out there to think about it. Here's another set of numbers. 1, 3, 7, 15, 31. Do you see maybe a pattern? How about those numbers? I'm going to go back to the original. Is there something happening here that would guide us? So I'm going to feature this. This is related to that first one. Here I have a sequence of numbers. So for Devlin, let's look at the patterns that we observe. 2, 5, 8, 11, 14. What is happening there? What should the next number be? Anyone? What would you imagine if you're thinking the same way I am? Well, what's happening here? As I go from 2 to 5, what have I done? Added 3, added 3, added 3. So add 3 to get to 17. That one's easy. It's an arithmetic sequence. You may have studied those elsewhere. You might not know it until you start subtracting the 5 minus 2, the 8 minus 5, the 11 minus 8. If you do that, you see all the differences between them of 3s. Of course, if you do that again, you'll get all zeros. But this is an example of a tool looking at the difference operator. And some of you may have studied that in your mathematics classes. So here's another then. 1, 7, 19, 37, 61. That's a kind of strange one, isn't it? Nothing probably comes so as quickly to mind as maybe for the others, or at least some of the others. But what if we try this difference? What's 7 minus 1? What's 19 minus 7? It's 12. What is 37 minus 19? Okay, 18. So what do we see? 6, 12, 18, 24. Now the pattern is easier to discern. And we could do this again. If I subtract it, I'll always get 6. And if I subtract again, I'd get zeros. So we've made more sense about this pattern. We'd have a good projection that I should just continue to add 6 to get to 30, add that, 61 plus 30 to get to 91. So this is one of the studies of patterns of number sequences. Okay? You could do it with squares, 0, 1, 4, 9, 16, 25, and that will relate to our image here that we had, that their differences are odd numbers. And that's why when you add up the 1 and the 3, we'll get the 4, and the 1, 3, and the 5 will get the 9, etc. You could do the rows again, you'll get 2s, the rows again, you'll get 0s, and this leaves us in the corner with 0s, 1, 2. Here's the cubes. We could do their differences. What will we find? Those are those strange numbers I just said, or maybe a sequence that was less obvious. The 1, 7, 19, 37, 61. We could process again, we get the 6, 12, 18, 24. Do it again, we get the 6s and then the 0s. But if I go back to that, take a look at these numbers, 1, 6, 6, for the next question. All right, so back to this. What are these? 1, 3, 6, 12, 15. That'd be referencing 1 plus 2 to give you the 3, plus 3 more to give you the 6. You see these what? Triangular numbers a lot, and you're just adding one more. Okay, we'll try the... We did that once where we plugged in this again. Right, so I guess we'll just try that. And this is about the point where after 1 or 2 more sequences, first it says no signal, then keep your fingers crossed, it'll show the signal. And then I could do some juggling of a basic form. Okay, we are back to that, but I will segue very soon to more of the juggling forms. And here is a little bit on, that's interesting. Not sure what's happening there. First of all, I have 3 balls to juggle. And we're soon going to be looking at these patterns of a site swap notation. And if I would give that a rest, I'll pull it out and turn that in. So with these 3, I want to demonstrate some of what happens physically to the balls with certain patterns. So first of all, I could do this pattern where I am throwing it up and I have 3 balls in this cascade. I think I'll go ahead and move this to maybe be a little less in the way of the mic. And if you observe the ball itself, what is happening, start with 2. In the ideal 3-ball cascade that I had just done, you would have 2 balls in one hand, 1 in the other, and you will throw from that, probably your dominant hand, over to the side and catch it ideally over in the other after you've thrown here. So it would look somewhat like this with just the 2. This goes up. Okay, and if you think about what's happening in that process, as this ball goes up, it gets caught by the other hand, which then throws it up, it gets caught by this other hand. What kind of shape? It looks like an infinity or a lazy 8 on the side, right? Kind of this 8 side shape. There is another shape, like some of the demonstrations here, and this gets to where I'm not always just looking to juggle by the, the official form. The 3-ball cascade can be done this way, where you go from this side, rotating, alternating, throwing from the right, catching it over here on the left, there we go, out, and then throwing about at the middle line up to be caught here. I usually just do that the best if I'm aiming low, which is a little quicker and harder, but I somewhat am staying that way. When I throw it higher, I've learned, for whatever reason, to not make that figure 8, but to more of an L shape. I move over with the right hand, throwing it straight up so that I'll be able to catch it right below. And then I have to get this hand over to throw it straight up to catch it on the right. It can be a little clunky, and you might find this for yourself, but this is some of the minutiae that you need to go to. Again, try Taylor Tries, or from Taylor Glenn, for some simple demos of these kinds of processes in tutoring. But here I'll go ahead and show you that, where I'm really making L-shaped movements of the balls rather than the figure 8. So if I move over and focus on just catching it by moving and walking with it in my little joggling, walking here, you can see that the movement was much more of that L shape. Now there's a lot of detail for what you do when you want to juggle 4 balls. For moving up to 4, it's not the same motion. You don't cross over and catch it with the opposite hand. You keep it going with the fountain, usually is the next step, a 4-ball fountain, and where each hand throws it to that other hand. And so you throw these, and if I would demonstrate it, I'll go by that rule of a touch is as good as a catch, and I can do it. But I won't demonstrate that now, I'll do it afterwards, like way afterwards. But for right now, know that I will do the 4 fountain with scarves at the end, okay? A little bit different dynamic. If you do move to scarves, they're simple to buy. You can get them online easily, of various kinds. They have this nice quality that they don't fall to the ground as quickly as a ball would. So go catch, do your air resistance calculations if you wish. There's a lot of physics here too. So this is 3 scarves, and I'll just go ahead and say you do want to pay a little attention to where you're placing them so they don't get tangled on each other for the very first throw. Keep them a little bit separate. And then know that if I follow this approach of what is the ideal more sideways 8-figure infinity symbol, that I will throw it from the right hand over to the left. And it's a little different catching mechanism. But you can do that and you have more time to keep it up. And I won't try this for hours or minutes. At least you can keep it up for quite a bit longer. Again, I'll do the 4-ball fountain at the end. Okay, well, we'll see if that does want to re-engage. Okay, so we're at this point where I think I'll make the observation that you'll have your own schedule. I think this runs till 11. We'll see who would like to ask some additional questions at the end or come up for it at that point. So this is the issues of patterns. I'm going to go ahead and get into some of the other questions. Do you see any pattern in this transformation? This is the theme of compressing sequences. I have 0, 0, 0, 0, 0. You can see some 1s and 0s and 1s. I then write that. Do you see what's happening, especially with the coloration pattern underneath it? Sorry. There were 7 zeros and 8 1s, and then like 3 zeros and 3 1s, right? This is called run length compression. And we'll compress both the video and the slides as we go. But for that run length compression, you then are able to compress, especially for bits on a screen, into another image. And I will say that it's probably a mystery piece. Come at 1 o'clock and you'll hear more about the mysteries of mathematics, maybe with the mysteries of technology also being one of those that's often with us. I do have the USB drive. If this continues, I'll give that to you.
So if you open it up, I can get the right one. So it's on this one. It would be the final. You can see it in there.
Okay, very good. Well, as you transition to your classes, note that there is more juggling here. And actually, it's up right now. We'll see how that proceeds. So this is the 0, 1, 8, 27, 64, 125 cubes. It moved on to be the kinds of differences that led us to these numbers like 166. Remember those 3 that I gave you just a bit ago? Or a 1 and a 2 off to the side for the squares. This actually has compressed this long list of what could be an infinite number of cubes, or a very long line of, let's say, 100 cubes, down to just these numbers. Why do I say that? The next screen shows that. If I do these kinds of difference operations, and I focus on the 1, 6, and 6 in this way, how did I get the 1 and the 7 and 19? I subtracted the 27 minus the 8 to get 19. 8 minus 1 to get the 7. In a similar vein, You can add the 1 with the 7 to get the 8, 8 with the 19 to get the 27. And you could also start even just with this 166 and percolate from the left all of these numbers that get added to generate the rest. So in that way, I could compress an arbitrary length, 10, 100, 1,000 cubes into just this 166. I need to run through the process, recursively define this, but you can generate them all. So 166 generates the cubes, and 1, 2 generated the squares. So there are some deep connections. So one of the themes was surprising connections along the way. And one of them has to do with a screen of a Excel document where I would be glad to dig into the thicket of this with any math major that might be interested. It's more on kind of the undergraduate research type of topic. This was a part of the kind of math conference talks where there is a dynamic. And is it still portraying? Yeah, I'll go ahead and show you the Excel coming up from over here that you can change some settings. And if you look closely, you'll start to see like a 1, 1. But let's try a different sequence. I could do 1, 2 or 166. Let's just do 1, 2. I'm going to put the 1 and a 2 here in the yellow. These are the generators. And with the 1, 2, what do you notice about these numbers? If you're able to see them up front, what are these numbers above the red? 1, 3, 5, 7, 9, 11. What are those? The odds. And you add them up, and in the initial sum of odds give you, the first 3 gives you 9, the first 4 gives you 16, etc. You then have generated in red the squares. All I needed, though, was to enter the 1 and the 2. So that demonstrates that compression and then decompression. With an Excel sheet that automatically does the addition or subtraction. So I can also put in, you see the little cheat sheet. Here's 166 for the cubes, 114, 36, 24 for the fourth powers. So in any case, if you enter in here 166, you can see what you get. And I'm going to soon zoom out where you can see more about these initial and sums that are happening. If you look closely, you will see numbers like 1, 7, 19, 37, right? Remember those? We then add up the first 2, and we get 2 cubed. First 3, we get 3 cubed, etc. So the initial sum, starting from the beginning of that sequence to some point, isn't that interesting, will generate, maybe if we try one more time, and that'll be about enough of that piece. And so there's a lot of imaging that I will show you that happens as you change the particular initial sum, how far you go with it. I keep track below some of the middle sums. So if you check below it, instead of starting from the beginning, 1 plus 7 plus 19, but maybe 7 plus 19, you can get the 26. Or 7 plus 19 plus 37 gives you 63. The sums of initial and middle sums of different kinds sometimes match up. For the squares, I could find them. For the cubes, not so much. I will zoom out and just show you the impact of this, where I have a particular band of green colors and that red tail. And if I would go backwards, I can change the initial sum that I'm considering. And you might ask what the changes in the green patterns are. And I could tell you, maybe in another math seminar, but it is initial sums and middle sums being matched up by modulus. Are they divisible by what number? The modulus is 30 here. I'll drop that down. The modulus is shifting to 28, 27 in the upper left-hand corner. And you get different patterns. If you zoom way out, you can see a larger frame, and they don't show you as much of the numbers, but you see the patterns of the moduli. And this is an interesting variety of patterns. So these were the cubes. Does anybody know if you can add up 2 squares and get a square? 3 squared plus 4 squared is what? 5 squared, of course. What about cubes? Can you add up 2 cubes and get another cube? You can't. And it's because this red tail It never gets lit up with that initial sum up here matching one of the middle sums down below. There's a lot of deep math to that. A few simple slides that I would maybe dare show you as this stays would demonstrate that. We can do it with squares but not cubes. But you can experiment with why it is that certain patterns that for the cubes we do not have this ability for the red tail to match some of the green patterns of matching the modulus of the initial sum, the actual cube, with a cube down here. It doesn't work. So there's some deeper dive into the arithmetic needed. I am going to swap back and maybe show you one slide and soon bring towards an end. So if I would go to this point of looking at some patterns of juggling where you count all the different methods of juggling, I'll start about here and show you what they look like. All right, let's move back. Here we go. So there is an agreement between two kingdoms. One likes to have just one juggler at a time. The other always likes to have two jugglers. They're into duality and complementarity. And they're orderly. They always throw off a certain number of period of how many throws. They're 3, 3, 3, or is it like a 5, 3, 1 throw that we will soon see. They're sequential and complete. There's a bit of a theory behind the 13-ball cascade that is possible by humans, or this 30-ball cascade that only maybe the right robotic device could come up with. You can ask that question. It all sets down into this question of how high do you throw the ball? The 5, the 1, or the 3, high enough so that you can catch it 3 steps further. With the side swap notation, you're always alternating hands. 5 for one, 3 for the other, 1. And you get this to work out. Certain valid patterns. And as you work through it, this is what the 5, 3, 1 looks like. And you can try others. Here's some other period 5, meaning we need a 9, and then a 0 means there's no ball there, and then a 1 as you alternate, or a 1, 2, 2, 2, 3, 3, 0, 5, 2, 0. There's a lot of juggling that's possible. You ask me how many I could juggle or how many people could juggle, you start to see that with site swap notation. So if you go back to this story that I was just telling you, that you have these two kingdoms, Onam and Lod, where in the annual juggling period you start off with 1, like the number 3 cascade, or 4, or 5, or the 1, 2. You know, you have different methods. If they are legit, they would orderly go through the period for the year, and they will always start with 1 ball, or then 2, or 1 period, 2, 3, and they start with 0 balls, 1, 2, and 3. And this is what it looks like in their kingdom of Onam, where one person does their period 1. This is the 0 site swap juggling. This is the 1 ball site swap. Every throw of 1. Back and forth, left and right. And the 2 is just redundant because you're kind of throwing it to yourself. They don't count it, they don't move. And the 3 cascade is here, and the 4 ball, you can see the fountain right there. So these are the period 1s. These are 2 others with the period of 1 as well, but they're 2 different patterns. There's 5 over here and 5 over there. And the last slide that I'll show you is that when you bring this up, we'll maybe try this one time more. When you ask the question whether they could go to period 3 in year 3 and match up all the possible ways to do 5, 3, 1 and other period 3 juggling forms, starting with 0, 1, 2, 3 balls, could they have a performance structure from Onam, where they just have 1 juggler, that matches for that ceremony the same number of juggling performances done by the 2 performers in Lod that like to have duality, they perform together? Well, it's not possible. And it comes down to the basic result I just showed you, that those cubics, 2 cubes don't add up to each other. You can also translate it into initial sums not matching middle sums. And yep, we'll see if it does want to progress through this way. It would be, okay, there we go. Okay. Here's some year 2 options. Year 2 options again. Year 3. And I will bring it to this point that for period 3, you see these numbers of possible 0 ball, 1 ball, 2 ball, 1 sub 19. And when they try to add them up, they won't match. So if I would jump, and this is the one working off this slide. Is it this computer now?
Yeah. Do you want to go back?
No,
to
this is
video?
fine.
Okay.
Yeah. Okay. And so we don't know what's going to happen with the 3-year. I will go ahead and say, is this advanced?
So, yeah, there we go. So this is a question about possible political coalitions, which surprisingly has connections to juggling. Learned it from, I believe, a former speaker here for Math Day. Ezra Brown co-wrote, also, who did you have? Let's see, math calculator, John, math magician. His partner, Ezra Brown, wrote Biscuits and Number Theory, and it was from him that I learned about this connection to bins and balls, that political coalitions can't be lined up in a certain way because of this relationship of how two squares add up to a square, a sequence of odds matched for the initial, middle sums and initial sums, but the cubes don't work. It's called something deeper. It's here that I start to ask the question, how many of you are a math major? Anyone? Where you might recognize this word, TSA. It's an acronym for the following are equivalent. You recognize that phrase, the following are equivalent. So there's a connection between sorting bins or political coalitions here, also to the connections to initial middle sums of odds, and something with Pascal's triangle. But I'll show you at the very end, this particular connection is called FLT. I'm throwing a lot of acronyms at you. Anybody have an idea? And I know if I ask Dan, you would give the answer because you're a number theorist. It's something special in a higher level number theory course that you might take. FLT. It has to do with these, yes, it's fine to get Pythagorean triples. We can't do it. We can match up the sums. We can take away the initial odds and get the middle sums matching the initial sums like these. 7 plus 9 is 16 is what the initial sum 1357 is. But you can't do it with cubes. And that is called Fermat's last theorem. If you ask a number theorist, they'll tell you a lot about it. It was just as I was a graduate student that it was both the unsettled question, we weren't sure if it was unsolvable, as Gödel would say, like we do not have the right axiom, but then finally Andrew Wiles came up with his sketches of proof that became the final proof, that you can start to equate these. The following are equivalent. It would be about the last major push before one last demonstration. These look equivalent to you? If you do your algebra, could you go from line 1 to line 2? Is there a pointer on this? Yeah. I'll try, but I don't also want to stop, so let's try there. So just subtract the b to the n on the left, right? So those are equivalent. It can be shown to be equivalent, just as I showed you, that the initial sum of the odds to give you, the 3 odds to give you 3 to the square will match then the initial sums and middle sums. When you subtract that initial sum minus that initial sum, they come out to be a middle sum. So those are equivalent. And that was needed for the juggling packs to work. And so it all boils down to Fermat's last theorem. What was that? Well, I said earlier in the story about these two kingdoms that it was Tamrick who studied it. It was really Fermat's result that he projected after his readings, the book by Fantis, that you can't extend the Pythagorean triples to cubes or fourth powers and beyond. And it would be really nifty if somehow there would be a way to see a visual proof for it. And that's why he couldn't fit it in the margins. And this kind of work, just as a real going out on a limb, maybe there could be a visual work with the Pascal's triangle that relates to these initial middle sum diagrams that would show a connection. I'm going to end up with the final word on certainty and create a surprise in the last minute or two that I'm extending to where I began, I guess. And the first one is there's lots of surprising connections in math when you study it, and even between lots of different disparate areas. There's also sometimes surprises of assumptions. So I'm going to go back to this. The sum of the measures of the angles of triangles. It's certain, right? They have to be 180 degrees. But what was one part of that construction? I drew the parallel. Go to a person named Gauss. Anybody hear of Gauss? Math majors, maybe Gauss. So in the late 1700s, early 18, he was able to offer so much to math. You might have heard about adding 1 plus 2 plus 3, the triangular numbers, up to 100, and how he solved that as a student. But another different kind of test with triangles, he would, in the Alps, check from mountain peaks to measure angles between certain mountain peaks. And you know what? They didn't add up to 180 degrees. And they couldn't. Why? Because you're on a sphere, so you have to check your assumptions. And on this sphere, for this equator, which seems to be a straight line when you're on the equator, just going around straight around the Earth on a grand circle, you can go north a little bit and try to draw another parallel horizontal type line. But what? You can't. They're actually circles up here. If you try to go parallel like this, they're going to meet, and you don't have parallel lines. So because of that, you start to see things like this is also a triangular shape in this image. If you go from the 90 degrees up at the equator, how much is this? 90. If I look at the initial prime meridian, this is 90, coming straight down, longitude with the equator. And up at the top, that would be 90. So they add up to 90 plus 90 plus 90 to 270. You have an excess, and Gauss measured that excess. Later, we developed the non-Euclidean geometries in the mid-1800s more thoroughly. Final little demo. Check your assumptions in everyday life. So I'm going to tell a story of a different shape I could try to juggle. What is this? Geologists, what is it? A geode, okay? And on this geode, I couldn't get enough geodes to juggle. Found this in Arizona, in the Navajo reservations, the Dene. And it was close to uranium mines off in the distance. Anyway, but just to make sure I'm okay, geodes, you have them around, you cut them up, they look pretty. I'm going to pull out my Geiger counter here and do a little test. I'm going to get out the Geiger counter and see if I have any of that uranium. This is a different take on math day. What do you notice? Oh, it would be bad if there were uranium dust on here. However, be assured, it's not coming from the geode. Where is it? You see this nice shiny, I'm not going to juggle this plate. It's called Fiesta ware. Any of you have it? It's a fine demonstration piece in physics courses. It has uranium in it. It's in the glaze, so it's not something you could breathe. You don't want to digest it either. But it's emitting some of these alpha particles. However, do also rest assured that in case you go check your cupboards and you find one of these, that actually with my assumption was if the Geiger counter shows something, it's definitely in the geode, it's from that uranium mine, right? But instead it's in the glaze. But if you do have it in the cupboard, you're not going to get the exposure. It gets mostly picked up by wood very easily. So when you look into anything, look for surprising connections and that creative surprise, maybe surprising assumptions. How do we have to change the assumption about the parallel? And for the spherical geometry, that's different. And also, maybe there's something hidden in your design. I will finish with the 4-scarf cascade. So, can you teach an old dog new tricks? I just looked this up last week on how you do the balls for, and I can do it, I can touch them. But at least I can make maybe the flash and then maybe do more with 4 scarves. So at this point, you saw me earlier do the 3-scarf cascade. Here's the 4-scarf fountain. And so you start off just knowing that you alternate hands like you tend to do with side swap. There are other options. And you will go ahead, and I'm going to keep those separate. There we are. Have that ready. I will alternate them, but I will also keep them in the same sphere. If we're lucky, they say jugglers always have 3 tries. Yeah, that's right. The 3 try of getting this to release. There we go. So that is the idea. And I think I caught them, so I guess I'm done. Thank you. So with my trying, feel free to come up. You'll probably be very similar to what I could do. Okay. Thank you for your time. All right, very good.